Factoring. Taking polynomials apart into their individual pieces that could be multiplied back together to create the original polynomial. It's extremely common in higher level algebra. We do it all the time. And when they're small, when they're quadratic, when there's a greatest common factor, it's easy. In the case of this basic quadratic, all I need to know is what two things multiply to make 10 and add to make 7. Come on, give me something challenging. Why? All right, we need to take it apart. Let's do it step by step, piece by piece. Let's peel back the layers of this onion. First detail, the fundamental theorem of algebra tells me that since this is a 4th degree polynomial, there will be 4 factors. That's how many answers I'm looking for. But I don't have any nifty tools like difference of squares or difference of cubes or star method to get something this big apart. Instead, what I have to do is I have to find potential factors, potential roots, and I have to see whether or not it's right. The rational root theorem narrows down the jillions of potential factors and roots down to a list that any rational roots have to come from. See my smartering video on rational root theorem to understand how it works. Being intelligent says if there's a greatest common factor in the original polynomial, factor it out. There isn't this time. The rational root theorem says take the constant term and factor it into every potential number that multiplies to make 84. Take the leading coefficient and take every potential number that multiplies to make 6. And the rational root possibilities are made up of every number that's this over this. Man, I love being able to do that. Problem, that's a big list. Oh wait, some of these are duplicates. That gets us down to only 25 answers. Don't forget, because there are negatives up here, positives and negatives are both possibilities. So we've narrowed it down now to 50 potential rational roots. That's still too many! You're right. Now be advised, my high school math teacher forced me to check each and every one of these until we found a solution. As you'll see here in a minute, once you find a solution, you've narrowed down from the original polynomial and you can work from there. But I've got an idea. Each of these is supposed to be a potential root, right? And it's a root because if this thing's equal to 0, it's the x value that makes that turn to 0. Shouldn't we be able to see that on a graph? Here's the graph. Can you see a place where maybe there's a root? Maybe there's a 0? Maybe there's an x value that causes this function to have 0 as its output? Can you see an x-intercept? I can, and I'm not even using modern technology. I'm using primitive technology from all the way back in the 1990s. Looking at this graph, I can clearly see an x-intercept that's probably at 3. 3, it's probably an x-intercept. It's probably one of my roots. It's definitely on my list that I accidentally erased. So, how can we check to make sure it really, really is one of the original factors roots of this polynomial? If only I had some test. I do. It's called synthetic division. It's how I divide something out of a big polynomial and do it quickly by having everything in its place. Go back to the synthetic division video if you don't remember how to do it. If I synthetically divide x minus 3, because that would be my factor, then that means I'm dividing 3, the root, out of these coefficients. Let's see if it works. Ha! It worked! It worked! It worked! We got no remainder. And with no remainder, it means that 3 as a root, or x minus 3 as a factor, factored out cleanly, divided out cleanly from the original polynomial. And it left us with remaining, after x minus 3 is divided out, 6x cubed plus 47x squared plus 99x plus 28. Remember the fundamental theorem of algebra told me I have to have 4 answers? We found one. It's 3. Now what? Now the short answer to the question, now what, is what remains is still big. This is still a cubic function, still not easy to factor, not by any of our recipes or anything like that. So the short answer is start over. Do the rational root theorem again on what remains, figure out which one seems like a good possibility, and keep going from here. But if there were roots of this and we got one out, won't all of those roots still be inside here? We can work from our original list. We can work from our original graph. Working from the original graph, I can see that there was a pretty good possibility at -4 as well. So let's go check -4. Come back to me. So let's take the original polynomial and check it at -4. But wait. If I divided x minus 3 out of the original polynomial and got this, all of the remaining factors and roots are still in here. I don't have to test the original polynomial. I can test the new one that I got as a result from my previous synthetic division. And that's going to be simpler, shorter, and it's going to narrow things down further. Let's synthetically divide this by my new possibility, -4. Yes! No remainder. -4 is another one of my solutions. Here we go. And now we have to start over again. No! We don't have to start over again. The reason it was so important that I check from the remainder of what had been factored out rather than from the original is because I keep taking factors out and being left with workable stuff. You know what's left now? 6x squared plus 23x plus 7. It's a quadratic. That's all that's left. Will the star method get it apart for me now? Yes, it will. And it found me my remaining two factors. And since I have the remaining two factors, and those are equal to 0, just like the original polynomial was, the zero products property says I found my other two answers. 2x plus 7 equals 0 would solve to make -7/2 as one of my roots. And 3x plus 1 equals 0 would solve to -1/3. This is a lot to remember, and it's hard to remember in the moment when you're doing all this work. But I don't have to use the rational root theorem and synthetic division to find every factor. I only have to use rational root theorem and technology and synthetic division to find enough factors to get me down so that what remains I can do by the old methods I spent a long time learning long ago. Now there is a reality to be aware of. The rational root theorem and this whole synthetic division process only finds us the rational roots. If there are roots that are irrational or imaginary, they won't pop up there. And what will happen is you'll get down to that final quadratic and you'll discover that it's not factorable, at least not by any easy method. Good thing we have our old friend the quadratic formula. It will find us irrational and imaginary roots that we can also put down here as the last pair of answers. And because the quadratic formula always comes up with two answers, that's why irrationals and imaginaries always come in pairs. This is a lot of stuff, so let me sum it up. If you need to factor something huge, something that is higher degree than quadratic or the simple cubics that we can do, first, this is always first. If there's any greatest common factor, take it out first. It makes everything else simpler. Next, use the rational root theorem to identify any possible roots, but that's just the whole great big list. You're then going to use technology, a TI calculator or Desmos or something, to narrow down that list to likely candidates. Then, once you have some likely candidates, pick the best one and test it using synthetic division. No remainder? Awesome, you found one. Remainder? Well, you screwed up, go try another one. What remains is what's left from the original polynomial. If you have to, test another candidate against what remains. But if what remains is quadratic, then you can factor using your ordinary tools, or you can even use the quadratic formula to find the remaining roots. And then the final step, dance.